Good morning, everyone, and welcome to the conference on stability, quantization, and randomness in symplectic geometry. I am Antonio Bru, the Dean of the School of Mathematics of the University Complutense of Madrid. My right is Professor Otto Rutwig Campoamor, head of the Department of Algebra, Geometry, and Topology, and in my left is Professor Álvaro Pelayo, main organizer of this conference. Thank you very much. As the dean of these prestigious institutions, it's an honor for me to stand before you today and extend my warmest and most sincere welcome to our school, our university, and our city, Madrid. As some of you may know, our university is one of the most prestigious in Europe. With a history of over 5 centuries, our university has witnessed the passage of a vast number of generations of professors and students through its classroom who have deepened knowledge and passed it on from one generation to the next. The Complutense University has produced 7 Nobel laureates and many distinguished researchers and professors throughout its history. Among those professors, we can find Professor Pedro Luis Pérez, a member of the Academy, who is a highly recognized Spanish geometer and central figure in Spain. This conference is dedicated to him for his dedication to this field and the significance of his work, and I sincerely appreciate his presence at this conference. Geometry has long been revered at the foundation of mathematics, and within this vast field, symplectic geometry stands as a captivating and profound branch. It explores the symmetries, structures, and dynamics of a space, unearthing hidden connection between algebra, analysis, and topology. It's a discipline that unveils the beauty of our physical world, and its impact reaches far beyond the realm of mathematics. Each and every one of you possesses expertise that spans a wide range of subfields. We have a unique opportunity to engage in fruitful discussion, share innovative research, and foster collaborations that will undoubtedly contribute to solving important and intriguing current problems in symplectic geometry. Throughout the course of this conference, we will explore the beauty and elegance of symplectic geometry, discussing some fundamental principles, latest development, and promising applications. It's an opportune moment for all of us to engage in stimulating discussions, exchange innovative ideas, and foster collaboration that will further advance our understanding of this fascinating discipline. We are fortunate to have a distinguished panel of speakers who will share their expertise and insights during the various sessions and courses of this conference. Their profound knowledge and research contribution have significantly enriched the field of symplectic geometry. I encourage each one of you to actively participate, engage in fruitful discussions, and seek guidance for these experts who have graciously agreed to be a part of this event. To the participants, I extend a warm welcome. Your presence here reflects your passion for knowledge and your commitment to advancing the frontier of mathematical research. This conference is an extraordinary opportunity for intellectual growth, where you will have the chance to interact with some of the brightest minds in the field. I encourage you to actively participate, ask questions, and engage in discussions that will expand your horizons and challenge your thinking. I would also like to express my sincere appreciation to the organizing committee formed by Professor Pelayo, by Professor Otto Rutwig Campoamor, Professor Diaz-Cano, and Professor Manuel de León, whose meticulous efforts have brought this workshop to fruition. Your dedication and hard work are commendable, and I'm confident that the program you have crafted will foster a dynamic and enriching environment for all participants. I also would like to express my gratitude for the funding of this conference provided by Professor Álvaro Pelayo Projects. On May 31, 2022, the BBVA, Banco Bilbao Vizcaya Argentaria Bank Foundation announced that it had awarded 35 research grants for scientific projects in the areas of mathematics, climate change and ecology, and conservation biology, biomedicine, social science, and philosophy. A total of 35 projects were selected among 620 submissions, including 4 projects selected in the area of mathematics. One of them is Álvaro Pelayo's project, held at the School of Mathematics at the Complutense University of Madrid, with title From Integrability to Randomness in Symplectic and Quantum Geometry. Really, only 4 projects in mathematics for entire Spain is a great pride for our institution. The announcement of these awards was covered in the mainstream Spanish national press, including El País, El Mundo, ABC, and La Vanguardia. This project is providing the main funding, I remember, for this conference. Finally, I wish to emphasize the importance of collaboration and networking during this conference. The connection you forge here have the potential to transcend this event and lead to the lifelong partnerships. Together, we can push the boundaries of symplectic geometry, unravel its mysteries, and unlock new avenues for exploration. The School of Mathematics takes great pride in hosting this conference, and I want to express the full support of our school and the Complutense University for the realization of this conference. Unfortunately, I have to leave now, as I have an important meeting for the school that I cannot miss. We'll meet again during your stay at our school. I hope you feel at home, and if you need anything, please don't hesitate to ask. Now, I have Professor Pelayo have the floor. Professor Pelayo.
Okay. Can you hear me with this? No. Can you hear me now? Yes, so the microphone works now. Okay, very good. I think it works now. Thank you very much. Dear Dean of Mathematics, Vice Deans, Chair of the Department of Algebra, Geometry and Topology, colleagues and friends, thank you for your presence here today. I would like to enthusiastically welcome Professor Garcia Perez and his daughters to the Complutense University. Welcome also to all participants, relatives, friends, and everybody who has taken the time to be here with us today. This meeting is possible thanks to the very generous support of the BBVA Foundation, who is providing all funding for the conference through my grant, as the Dean said, with title From Integrability to Randomness in Symplectic and Quantum Geometry. Without the support of the foundation, we would not have been able to do it. I would like to give special thanks to Laura Poderoso, who is the Vice President of the foundation, for her support. I would also like to express my deepest gratitude to our Dean, Antonio Bru, who is allowing us to use the Miguel de Guzman classroom, to have this conference, and for being here to open this ceremony, despite being so busy. Thank you, Antonio, for your continued and effective support, and for all the important work you do for the School of Mathematics and for the university. I would also like to thank our department secretary, Teresa, the School of Mathematics manager, Belen, and the entire team in charge of the administration of my grant for all the work they've done to make this meeting possible. Thank you to all the computing staff who have helped us with the preparation of the meeting, and to all the university personnel called past here, who have helped us or are helping us during the meeting in any way. In particular, thanks to Miguel and the entrance door staff for installing portable air conditioning in this room, and Belen and the Dean for allowing it. Last but not least, I would like to thank very much the other organizers of this meeting, Rutwig, Campoamor, Manuel de León, and Antonio Diaz-Cano, for the important work they've done to make this meeting possible. We have a great conference ahead with distinguished speakers who will tell us about important topics at the forefront of research in dynamical systems, symplectic geometry, mathematical physics, integrable systems, and probability. I hope you will enjoy it, and I defer now to Professor Campoamor, who will say a few words.
Bueno, puesto que me toca a mí hacer la presentación del profesor García Pérez, a una muy breve alocución. Evidentemente es un privilegio poder hacer, como he dicho, esta alocución inicial de un tipo de proyectos que son innovadores en esta facultad y sobre todo en cuanto a la disciplina a la que se han concedido, que son las matemáticas puras, que constituye una rareza en su naturaleza, dada, digamos, la tipología de proyectos que se suelen conceder y que, por tanto, es un honor para esta facultad el poder presentar proyectos de este tipo, y no podemos por menos que congratular al recipiente principal de dicho proyecto, que es el profesor Álvaro Pelayo, el haber conseguido lo que es un hito fundamental y que sería deseable que los estamentos ministeriales tomasen nota de este tipo de proyectos y su importancia y relevancia de cara a la proyección científica en este país. Por otra parte, esto distingue tanto a la facultad como al propio departamento, que incidentalmente represento en estos mismos instantes. Es evidente que lo más pertinente es que no hay un modo más honroso o más privilegiado de iniciar un congreso de este tipo que cediendo la palabra al profesor García Pérez, digamos, en honor de quien se hace este congreso, sobradamente conocido por sus logros científicos y a quien tratamos humildemente de, digamos, agradecer todo la escuela que se ha creado a su alrededor, no solo a partir de la Universidad de Salamanca, sino con una expansión nacional, y que además tratamos, nuevamente humildemente, de congratular por su 85º aniversario. Sin más dilación, me gustaría cederle la palabra al profesor García Pérez, que tiene preparadas unas conmemorativas palabras para iniciar solemnemente este acto. Muchas gracias por su atención.
Queridos participantes, casi sin darme cuenta, han pasado ya 60 años desde que me ocupé por primera vez de la aplicación de los métodos de la geometría simpléctica a la física de campos. Fue este el tema de mi tesis doctoral que me propuso y dirigió el que fue mi principal maestro de entonces, Juan Bautista Sancho Guimerá, profesor de esta Universidad de Madrid y posteriormente catedrático de las universidades de Barcelona y Salamanca. La idea originaria de este proyecto era muy sugestiva. La formulación lagrangiana de un campo clásico debería ser ya hamiltoniana al entenderse como la variedad simpléctica de las soluciones de las ecuaciones de campo. Y esta, a su vez, debería poder expresarse de un modo cuántico, eligiendo la norma adecuada sobre el álgebra de Poisson de los observables clásicos. El tema era de mucha actualidad en esos años, tras la publicación por Irving Segal de una serie de inspirados trabajos sobre la cuantificación de la variedad de soluciones de la ecuación de Klein-Gordon no lineal, dotada de la métrica simpléctica definida por el propagador asociado a dicha ecuación. La parte clásica de este proyecto conseguimos desarrollarla satisfactoriamente, permitiéndonos entrar de lleno en lo que ha sido uno de los principales capítulos de la mecánica geométrica, la formulación multisimplética de la teoría clásica de campos, a la que he dedicado, junto con algunos brillantes colaboradores, muchos años de mi vida. Desde entonces, la mecánica geométrica se ha desarrollado ininterrumpidamente en muchas direcciones y temas, de lo cual es una buena muestra la presente conferencia que con tanta generosidad se me ha dedicado con ocasión de mi 85 cumpleaños. Agradezco ilusionadamente este gran honor que deseo compartir con todas las personas que han hecho posible, de alguna manera, el desarrollo de nuestro trabajo. Muchas gracias.
Thank you very much for your words, Professor Pedro Garcia. And I declare this workshop on symplectic geometry officially open. Thank you once again for joining us, and I wish you all a productive and fulfilling experience. Thank you, Professor. Thank you very much.
Thank you, Dean. Thank you very much for your presence here.
Muy bien.
Now you have to present my talk. Now you have to present my talk. Tienes que presentar mi conferencia. El nombre, ¿te acuerdas?
No.
Me lo voy a poner aquí. Ok. ¿Os podéis sentar? Solamente se está oyendo. Te sientas y presentas. Te sientas y... Ok. Ok, Rutwig. Ahora empiezo yo. Sí. ¿Te vas a quedar aquí?
Now,
What is this?
once,
Ah, ok. Ok.
once the official opening closed, I have the honor of presenting the first of the speakers, which is, of course, the recipient of the program, Professor Álvaro Pelayo, who will speak about integrability, stability, and randomness in symplectic geometry, recent progress and future venues.
Okay, thank you very much, Rutwig. Thank you for being here. Thanks a lot. So I assume everybody can hear me okay, right? The microphone is working? So if at some point it doesn't work, you can let me know. Okay, so the title of my talk is Integrability, Quantization, and Randomness in Symplectic Geometry, as Rutwig said. This talk and this conference are dedicated to Professor Pedro Luis Garcia Perez from Salamanca on his 85th birthday. And this is a colloquium style talk, so I'm going to be presenting topics that I've done throughout the years. In particular, I'm currently funded, as it has been said, by the BBVA Foundation, but previously I was funded by the United States National Science Foundation at various institutions, and part of the work that I'm going to be discussing today has been done at Berkeley, MIT, IAS in Princeton, Washington University, and UC San Diego, all institutions to which I'm very grateful for the support they gave me. Okay, so the most important thing perhaps of my talk is that it's dedicated to Professor Pedro Luis Garcia Perez, who has been a pioneer in the early Spanish school of differential geometry. In the 1960s and 1970s, when circumstances in Spain made it difficult for Spanish mathematicians to publish in international journals, Pedro Luis published papers in leading journals such as Communications in Mathematical Physics at the end of the 60s, Archive of Rational Mechanics and Analysis, and Journal of Differential Geometry. These are great achievements that I'm very proud to remark here. So congratulations, Pedro Luis, on your 85th birthday, and you have my admiration for your contributions to differential geometry and for the role you have played in the development of its interactions with physics, mechanics, quantization, etc. Okay, so this is a colloquium style talk, so perhaps many of you haven't. Of course, the speakers of the conference know very well what the word symplectic means and where it comes from, but since this is a colloquium style talk, I'm going to start by mentioning what symplectic means. So the word symplectic has its origin in a book on classical groups, a very important book by Hermann Weyl, who was a professor at IAS Princeton, and it derives from a Greek word which means complex. Now, there is also another field which is important to this talk, which is dynamical systems. So what are these fields? Dynamical systems studies the motions of planets, space shuttles, molecules, car, water, waves. And symplectic geometry studies a sophisticated notion of area in 4 dimensions and in general in any even dimension. And this area can be even negative. So this is a geometry which is not as intuitive as the geometry we are used to, but it has a different flavor, a completely different flavor, one might say. Okay, so the modern fields of dynamical systems and symplectic geometry, they evolved from the work of Henry Poincaré in celestial mechanics. And Poincaré viewed them as one field with integrated ideas. The developments after Poincaré is that these fields develop independently, but more recently, this common core has been recovered. So some leading figures at the intersection of these fields. Many mathematicians work at the intersection of dynamical systems and symplectic geometry, often using techniques from symplectic geometry to prove results about dynamical systems. This point of view is often called symplectic dynamics. And in 2011, 2012, there was a special year very precisely with this topic at the Institute in Princeton. And it was led by Helmut Hofer and John Mather. And as I said, the title was Symplectic Dynamics. And the goal of the year was to explore precisely the interactions between symplectic geometry and dynamical systems, and in particular, use symplectic techniques to prove theorems about dynamical systems. So where does symplectic geometry appear? Symplectic geometry, as certainly all the speakers and many participants will know, appears in many places. For instance, it appears in applied subjects like applied parts of physics, chemistry, and engineering, including, for instance, molecular spectroscopy, fluids, plasma physics, elasticity theory, mirror symmetry, robotics. And at a pure level, it's connected at a core level with major subjects such as representation theory, complex algebraic geometry, Fourier analysis, microlocal analysis. And we have experts, we have fortunate that for this meeting, we have experts in various of these branches. In particular, for example, I'm seeing my friend Tudor Rutwig, who is here, who has done many contributions to applied aspects and pure aspects of symplectic geometry. Okay, so what is a dynamical system? A dynamical system consists of objects which evolve over time, obeying some rules. For instance, this picture, what does it suggest to you? This is a pendulum, right? This is a simple example of dynamical systems, and these rules are often given by differential equations, and the solutions to these equations are called the orbits of the system. What is the goal of dynamical systems theory? Is to understand qualitative properties of orbits. For instance, shape are the orbits, circles, straight lines, parabolas, and long-term behaviors. For example, do the orbits escape to infinity? Here is an application of symplectic geometry to dynamical systems. Symplectic dynamics, symplectic geometry can be used to find optimal orbits which minimize fuel consumption for space missions. This represents a huge improvement of previous methods which find the orbits by trial and error. Okay, so this is an extremely important application, and in fact, there is a very interesting story behind all of this. I'm going to very briefly discuss space mission by Japan. So Japan Space Institute launched a big spacecraft into space, and it's separated into 2 crafts called Muses A and Muses B. Now the goal was to have Muses A orbit around the moon, but it malfunctioned and they lost it. Okay, so the only hope was to have Muses A orbit around the moon. Now the problem was that Muses A was not equipped with enough fuel to brake hard enough. So the hope was lost. Now, using basic principles from symplectic geometry and dynamics, the mission was saved. Okay, how? This is an idea of Belbruno. Belbruno's idea was to ignite muses A at the right time and place to send it to Lagrange point, to the Lagrange point, where gravitational fields of Earth and Sun cancel out. And there was enough fuel for this. So, in the end, there was a success. And Belbruno's method can be greatly improved using symplectic dynamics, ideas developed by Hofer and collaborators and many other people in what is called SFT. Okay, so for this talk, I'm going to focus on a famous type of dynamical systems, which are called integrable. And Pedro Luis, Professor Garcia knows a lot about these systems. So an integrable dynamical system is a type of dynamical system which has many conserved quantities. Okay, for instance, energy, momentum, and so on. So here is an example. What does this example look like to you? Like a wave, right? So this is an important example. It's the shallow water wave. It's a very important infinite dimensional example, which it took many years to know that it is integrable. Okay, so the subject of integrable systems, I assume I'm still being heard, right? Okay. The subject of integrable systems is vast, and it is spread over many interconnected areas, viewpoints, and so forth. For instance, it interacts with classical and quantum mechanics, Poisson geometry, Lie theory, semi-classical analysis, algebraic geometry. I see some algebraic geometers in the audience as well. Applied mathematics, KAM theory, even homotopy theory. So it's a subject that it is spread out over many branches of both pure mathematics as well as applied mathematics. Also, it is quickly evolving and making its way into even more mainstream aspects of research, such as the Langlands program, symplectic topology, mirror symmetry. I can tell you that on many occasions I go to talks on various topics, different topics in geometry, analysis, physics. For instance, yesterday I was at a talk organized by Marina Logares, who I don't know if she's here, and there was an integrable system in that talk. So they are, yeah, this was a physics-oriented talk, right, Marina? So they are, you can find integrable systems in many, many places. Now, in this talk, I'm going to focus on finite dimensional integrable systems from the perspective of symplectic geometry with an eye towards the spectral theory and semi-classical analysis of quantum counterparts, right? So I have been, throughout my career, I have been working on the interaction between these two subjects, symplectic geometry and spectral geometry, in particular quantization. And I know Pedro Luis shares the joy of these two subjects because he has made many contributions to symplectic geometry and also to the quantization part. Okay, so roughly speaking, I just told you that an integrable system is a dynamical system with many conserved quantities through the motion, okay? So, formally, what are these objects? So, we have two types, classical and quantum, okay? Classical integrable systems, they take place on manifolds like, for example, a two-dimensional sphere, like the one in the picture, and they are given on a space of dimension 2n by n functions. These are called Hamiltonian functions in honor of Hamilton, which take value in R. One of these functions is the energy function, and the other n-1 are quantities which are conserved throughout the motion. And it is known that you can have at most n-1 conserved quantities in addition to the original energy function, okay? So the system is called, in some sense, integrable because you find the maximum number of these conserved quantities, which in physics and also in mathematics, they are often called integrals. That's why the system is called completely integrable, because it has as many integrals as possible. Okay, so this is the size the side of classical systems, okay? Manifolds and functions. Now we go to the quantum side. So on the quantum side, we have quantum integrable systems. They take place on Hilbert spaces, okay? And now, instead of being given by functions, they are given by operators of various types, like Beresin-Topliss operators, pseudo-differential operators on H, etc. And to these operators, there is associated a spectrum, which is given by the joint eigenvalues of the operators, okay? So the quantization method of Costa and Soriao construct a quantum system from a classical one. In Spain, Garcia Perez, to whom we dedicate this conference, has been a leading expert and central figure of this theory. So I'm going to tell you the 3 goals for this talk. The first one is to understand more about classical integrable systems. This uses symplectic geometry. The second is to solve the inverse spectral problem for important classes of quantum integrable systems. This uses spectral geometry. And the third talk is to announce a proof of the random Arnold conjecture for symplectic twist maps, which is posted in the archive as of this morning. With Freidun Rizahanlu, but I think Freidun is not here now, right? Freidun? No, Freidun didn't. Oh, you made it. Welcome. So Freidun is giving a mini course on our joint paper in which we prove the random Arnold conjecture in the probabilistic setting for symplectic twist maps. And there is going to be a mini course, and now if you want, you can check the paper in the archive which we posted yesterday. You saw it posted, right, Freidun? Yes, very good. Okay, so the first and second goals of this talk are very related. The classification of classical systems and the inverse problem for quantum systems are related at a deep level, in the sense that in order to solve the inverse problem, one must first solve the classification problem. And I'm going to explain why this is the case next. And as I mentioned, I'm going to leave the random Arnold conjecture to Freidun's mini course, but I highly recommend that you attend because I think this is a very interesting topic, and Freidun is an excellent lecturer, and I'm sure it's going to be a great mini course. Okay, so I'm going to briefly explain the symplectic inverse spectral problem for non-experts, okay? What is this problem about? So imagine that you're reading a newspaper in your living room, okay? And your daughter is playing her new drums in her room, but you have never seen the drums, okay? They are new, you've never seen them. Now you listen to the superposition of frequencies emitted, okay? This looks like the spectrum, okay? This is a set of points, in this case, in the plane. And now the question is, can you draw the shape of the drums? Now keep in mind, you haven't seen the drums, so you want to know if you can draw the shape of the drums. And the answer is not in general, okay? This has been proven in the early 90s. However, wait, in the symplectic category, you can answer this question in some cases, and this has been a main focus of my research with various collaborators. Okay, so here is an example of solution to the symplectic inverse spectral problem, which we obtained in 2013 with precisely, I remember this proof, we made this proof in Princeton, in the institute in Princeton, where Logan Charles and Sam Bungok were visiting me. I was a member of the Institute for Advanced Study at that time. And during the summer, one of the summers of 2012, I think, we proved that if the system is integrable and periodic, then you can actually recover the system from the spectrum. So this type of results, they are surprising because you see the spectrum is a discrete set of points, okay? And then from that, you want to recover an entire system. So you want to recover, it's like if you want to recover the shape of a guitar from just measuring some frequencies, right? So that seems that in principle should not be possible. So in general, it is not possible, but it is possible to solve this if the spectrum we're talking about is the spectrum of an integrable system which such that all of its components are periodic. So what is the strategy to solve this? So there are two parts. The first part is symplectic geometry, and this is the part which connects with the first goal I mentioned, is classify integrable systems in terms of invariance. You learn that in order to recover the shape of the drums, there are 2 or 3 key things that you have to recover. These are invariants, which can be numbers, polygons, etc. And you have to use a spectral geometry to compute these invariants. You can still hear me, right? Yeah, okay. In the spectrum. So the motivation to solve the inverse spectral problem, one of the motivations comes from quantum molecular spectroscopy. So roughly speaking, can you hear the shape of molecules? Can you hear the orbits of molecules in 3D space? And this question arose from works in chemistry, physics, and in various contexts, in particular in the work of this group, Mark Child's group in Oxford, Jonathan Tennyson at University College, Frank DeLucia at Ohio State, Boris Zielinski in Dunkerque, and Mark Joyce in Grenoble. Okay, and there are many prior relevant results to our work, to the work I'm going to be discussing in this talk. In particular, to the spectral theory part, there is work by Charles, Gilleman, Moser, Sarnak, Sjostran, Ullmann, Weinstein, Seldich, Swirsky. On inverse problem, there is work by Colin de Verdier, Doisema, Gilman, Hermander, Weinstein on Fourier integral operators and spectral theory. Work by Doisemat, a very important paper by Hans Doisemat that I'm sure Pedro Luis knows very well on the existence of global action angle coordinates for integrable systems, and many other works by Hitchin. By the way, if I remember correctly, Marina's talk is about Hitchin systems. Is that right? Yes. So make sure to go to that. Then there is work of Eliasson, which is very important for my purposes and for my research, because Eliasson proved that non-degenerate singularities of integrable systems can be linearized. You have simple models which describe them. And then there is work by Aru, Gross-Sieber, Waltieri, and Seidel on many aspects like affine geometry and generalized complex geometry, etc. Okay, I'm going to say just a couple of words about to advertise further Freidun's talk. And let me start with the very simple result that classical important result by Poincaré and Birkhoff. It says that any orientation area preserving diffeomorphism of an annulus that rotates the boundaries in opposite directions has 2 fixed points. Okay? The generalization of this major result is due to Arnold, and it's called the Arnold conjecture in the 1970s, and this has generated an immense amount of research in symplectic geometry and symplectic topology. Okay? So Freidun and I started to work on this project around, if I remember right, around 2008, when at the time I was in Berkeley, and Freidun was there, and we started talking about this fascinating topic. And we proved in a paper that appeared in 2018, although the paper was ready much sooner, but it appeared in 2018, we proved that the random Poincaré-Birkhoff theorem holds. And a new probabilistic symplectic theory now leads to the theorem that Freidun is going to explain, which is more complicated to state, of course, than this. But essentially, the random Arnold conjecture holds for symplectic twist maps. And the proofs combine ergodic theory, probability, and symplectic geometry. And I'm going to leave Freidun to explain the details of this, but I highly recommend that you attend his mini course, because I personally find this to be a fascinating topic, the intersection of probability and symplectic geometry. And I remember talking to Pedro Luis on the phone that he was also, he also found this idea of combining symplectic geometry and probability at least intriguing, right? Yes. Okay, so for the remaining of the talk, I'm going to focus on explaining a little more about the first 2 goals in some more depth, okay? So, I'm going to now give mathematical definitions so I can formulate some theorems more precisely, okay? For the precise versions, of course, you can look at my papers. But we start with the basic notion of symplectic manifold. So this is as follows. We start with a smooth manifold, and a 2,4 omega on M is symplectic if the antisymmetric bilinear form, omega M, given by restricting the two form to each point and each tangent space, is non-degenerate. Okay? And also we require that it's closed, that is the differential of omega is 0. And the pair is called a symplectic manifold. And you may wonder why I put this picture here, right? The reason is that this is one of the simplest examples of symplectic manifold. It's a surface endowed with an area form, okay? An area form is the same as a symplectic form, okay? So symplectic geometry in dimension 2 just cares about the areas, okay? Now, what are examples of symplectic manifolds? Examples are, as I said, S omega, where S is any surface and omega is an area form. R2n with the standard symplectic form, dx1, which dy1 plus dxn, which dyn. And T star x, the cotangent bundle T star x of an n manifold x with the cotangent bundle coordinates. And this third example, everybody that works in physics and everybody that knows physics, like Pedro Luis is an expert, knows that the cotangent bundle is perhaps the essential example of symplectic manifold in the non-compact setting. Okay, so I'm going to explain very briefly a geometric interpretation of symplectic, okay? If we start with a symplectic manifold and omega is a symplectic form, closed and non-degenerate, do you agree with me that I can integrate the form omega, which is a 2 form, over the surface, which is 2-dimensional, right? So let's call this the symplectic area of the surface, okay? So the closeness condition says that, the closeness meaning d omega equals 0, says that the symplectic area is unchanged when deforming the surface by keeping the boundary fixed locally, of course, locally. So here, suppose that this S and R are two very small surfaces that have this boundary C. So they have the same symplectic area. So you can already tell this is very different from Riemannian geometry, right? This is a striking difference with Riemannian geometry. And the non-degeneracy says that you have an isomorphism between the tangent and the cotangent bundles. Okay, so here is a question in case you haven't seen symplectic geometry before. Is the 3-sphere symplectic? Is the 3-sphere symplectic? So the answer is no. Why? And this is linear algebra. The fact that omega is non-degenerate implies that the dimension of the manifold is even. Okay? So symplectic manifolds are even dimensional. So the 3-sphere, which is 3-dimensional, is not symplectic. Okay? Is the Klein-Bodel symplectic? This is easier. Because I told you that the symplectic form is the same area form as an area form. So the Klein-Bodel is not symplectic because omega is an area form. And if you take powers of the symplectic form, you get a volume form. If your manifold is of dimension 2n, you take n powers and you get a volume form. So symplectic manifolds are orientable. So orientable, even dimensional. And now this is harder. It's S4 symplectic. This is the 4-dimensional sphere. And this is, if I remember right, this was an exam question when I was teaching the course on smooth manifolds at Berkeley. So it's S4 symplectic. The answer is no, and the proof is that this is harder. You have to do some work. If the manifold has dimension 2n, since omega is symplectic by Stokes theorem, we have that the cohomology class of the kth power of the symplectic form is non-trivial. This means that the even dimensional, the rank cohomology groups, they are all non-trivial. So symplectic manifolds, they are topologically interesting. Okay, compact ones. Of course, you know that this doesn't work for R2n, right? But for compact ones, these even dimensional, the rank homology groups don't vanish. So is there any symplectic sphere? Now I did everything. Now the answer is you have almost no one, but no sphere, but is there one of them? S2, right? S2, exactly. So the answer is yes, only S2. Since the odd dimensional ones we can rule out because of dimensional reasons, and the even dimensional ones have zero cohomology. Okay? In contrast, in Riemannian geometry, the curvature is a local invariant. Now, what invariance, not in contrast, sorry, in Riemannian geometry, the curvature is a local invariant. So what are the local invariants in symplectic geometry? The answer is none. And the reason is that Darboux, in the late 19th century, proved that all symplectic manifolds are locally diffeomorphic to R2n with the standard form. So what does this mean? This means that this result means that in symplectic geometry, you cannot look for local invariants because there are no local invariants. Everything has to be global. And this is why it is often called symplectic topology. Okay? Now, I'm going to define now formally what is an integrable system. So the first thing is that the vector field xf induced by a smooth function on a manifold is given by this equation. Okay, you take the 2 form. Now you take the differential of your function, df, and that's a 1 form. Okay, and now, do you agree with me? There is a unique solution, xf, which defines a vector field. Okay? This is called the Hamiltonian vector field. And now an integrable system is a map, f1, fn, on a manifold of dimension 2n. And from the motivation at the beginning, you know why there are precisely n functions on a 2n manifold, right? Because we said that is the maximum number of functions that you can have. So this is an integrable system. If each function is constant along the flow of the vector field generated by any other function, and of course, they have to be linearly independent everywhere, right? Because if not, I take one and I start multiplying by a constant and no problem. I generate all the integrals you want, but not interesting, right? So I want them to be actually integrals, meaning that the vector fields they define are linearly independent. Okay. So this is the main object on which many people have spent. There are thousands and thousands of papers on integrable systems, and in particular, I have spent many years precisely trying to understand this concept, the concept of integrable system. Okay. Now I'm going to make an extra hypothesis for the talk, which is that this is technical, that the fibers are compact. Okay. Most of what I'm going to say requires that the fibers of this map are compact. For the differential geometers and the analysts, we know that if you are in a non-compact, if you have non-compact fibers in a non-compact setting, then Morse theory is very difficult to apply, and this causes technical problems. So I'm going to make this assumption. So why do mathematicians study integrable systems? Here is a favorite quotation of mine by Jürgen Moser in a plenary lecture at the International Congress of Mathematicians in Berlin. It is impossible to even touch on the many ramifications of integrable systems, okay? Es imposible incluso tocar, dar una pequeña idea de las muchas ramificaciones de los sistemas integrables, okay? And Moser continues that have evolved from the study of integrable systems. And Moser continues to say, most striking to me is the development of integrable systems some 30 years ago, which did not grow out of any given problem, but out of a phenomenon which was discovered by numerical experiments in fluid dynamics. Okay? And Moser continues to say, intelligent studies and deep insight open up to a novel field impinging on differential geometry, algebraic geometry, and mathematical physics. And we have experts on all these subjects in the audience, including applications in communications of fiber optics. So you can see, by the way, I highly recommend this article by Moser in the Proceedings of the International Congress in Berlin. Is an excellent read and very interesting. Okay, now let me mention very quickly now the historical definition of integral, which I already discussed. A function f1 is integrable if there are functions f2 up to through fn such that the joint map is an integrable system. That is, again, each function is constant along the flow of each other function, and almost everywhere these vector fields are linearly independent. Okay, so this is historically where the definition of integrable system comes from. Okay, people didn't say, well, let's take a map with n components on a 2n manifold. No, right? Historically, you start with a function, energy function on a manifold, and then you encounter the other functions which integrate it. These are the integrals, and you put all of them together, and the modern viewpoint has been to precisely consider the integrable system to be this joint map. Okay? Now, the most interesting features of integrable systems are in the singularities. Okay? So what is a singularity? A point M at which the vectors x1, xf1m, xfnm are linearly dependent is a singularity. Okay? Now, you remember this linearly dependence condition comes here, right? Almost everywhere, these vector fields are linearly independent. So almost everywhere, with respect, say, to the volume form induced by the symplectic form, almost everywhere linearly independent. So what happens? The most interesting features of these objects are precisely where they are linearly dependent, right? So these are the singularities. A singularity is a point where the condition of linear dependence, which happens almost everywhere, doesn't hold. And most interesting features of integrable systems are encoded in the singularities. Okay? So in this talk, singularities are assumed to be non-degenerated in a Morse-Bot sense. The precise notion is a little more technical because f is a function which takes values in Rn instead of R. Okay, so I think you agree with me, at least mathematicians agree with me, that this is a very simple object. There is a manifold and n smooth functions which satisfy these conditions. They are linearly independent, and each function is constant along the flow of every other function, right? Okay, so I'm going to give you some famous examples of integrable systems with explicit formulas. So here is one, the coupled spin oscillator, which is also called the James-Cumming model, which goes back to 1963. This is studied in physics papers by James and Cummings, for example. So how is this system defined? So you take coordinates x, y, z on the two sphere and uv on the plane, right? Here you have the picture, the two sphere across the plane. So you can see this is a manifold of dimension 4, right? You have a 4 manifold. And I'm going to endow it with the product symplectic form, which is the sum of the symplectic form on the sphere and the symplectic form on the plane. And now the integrable system is given by this function, energy function, and this integral. This function, u squared plus v squared over 2 plus z, and this is ux plus vy over 2. Now, those of us who work in symplectic geometry certainly recognize this as the momentum map. Certainly, Angel does recognize this as the momentum map of the rotational action on the two sphere about the vertical axis and the rotational action on the plane about the origin, right? So this is an integrable system. Now, another example is the spherical pendulum studied by Huygens in the 17th century. And this is defined on the cotangent bundle of the sphere and is given by by this function f1 as energy function. Here, theta and phi are spherical coordinates, spherical angles, okay? And f1 is the sum of kinetic energy plus potential. And this system is integrable, and the first integral is precisely given by psi phi, okay? So if you have seen the formulas before, you know them, and if you haven't seen them before, this is a little hint of the formulas, but I'm going to move to the next system. This is a system which I have studied myself a lot. Is the coupled angular momentum, which is another interesting example of integrable system, okay, of Sadowski and Zielinski. And this is defined as follows. On S2 with S2 cross S2 with coordinates x1, y1, z1, x2, y2, z2, the system is defined by these two integrals, okay, f1 and f2. The details of the formula are not important, okay? If you work on mathematical physics or symplectic geometry, you know the formulas, but I'm not going to. I just wanted to tell you that there are extraordinarily important examples from physics which are integrable systems, okay? In particular, you can see this is on a compact manifold in dimension 4. Okay, and this example from the point of physics is perhaps less relevant, but it's very important in other contexts like algebraic geometry and equivariant symplectic geometry, is the complex projective space endowed with the Fubini's 2D form. And this integrable system has these formulas, which I'm sure the algebraic geometers and certainly the symplectic geometers know. Each component is Zi divided by the sum from 0 to n of Zi squared. And this is induced by the rotational action of a torus on the complex space of dimension 2n plus 1. Okay? So these are 4 examples. Probably my favorite examples. I'm telling you some of my favorite things. And they are also very good to test computations and to test if you have some theory about integrable systems. These are good examples to test your theory with. So complex projective space, coupled angular momentum, James-Cummins system, and spherical pendulum. Okay? Okay, so the spherical pendulum, the coupled spin oscillator, and the coupled angular momentum systems are important integrable systems from classical mechanics. Indeed, symplectic geometry has its origins in classical mechanics, and much of its development has been motivated by it. Okay? Many works emphasize mechanical aspects of symplectic geometry, including some very well-known books by Abraham Marsden and works by Abraham Marsden, Lieberman and Marl, the book by De Leon Rodriguez. We have Manuel here, and we also have Tudor Raju here, who has a book with Marsden. Okay, so I recommend that you consult these works for connections of symplectic geometry to classical mechanics. Okay, so I told you what a singularity is. I'm going to tell you now what a singular fiber is. It's very simple. If a fiber of the integrable system contains a singularity, it is called singular. Okay? Otherwise, it is called regular. So here is in blue. In blue, here you have an example of a singular fiber. You can see it looks rather complicated, right? It's a 2-dimensional torus in which we take some circles, some cycles, and collapse them to a point. Okay, so this is an example of a pinch torus, and this is a fiber which appears a lot as a fiber of integrable systems. Okay? Now, for regular fibers, we understand exactly the theory. So each regular fiber is a torus. Remember, I'm assuming that the fibers are compact. Okay, to simplify, each regular fiber is a torus, and in a neighbor of each fiber, every integrable system has a local model, which is the cotangent bundle of the torus, and the formula for the system is just projection. Okay, projection from x1, xn, psi1, psi-n to psi1, psi-n. And there is a global version of this result by Dostjemat. So what does this mean? This means that the global theory in a neighborhood of a fiber, which is regular, is completely understood. Okay, this is this theorem. Okay, But if the fiber is like this, then this is much more difficult. Okay? In fact, the description of a neighborhood of this fiber in symplectic terms has been only done recently in a paper by Suri Tang and myself, and also there is a paper by Bolsinov, who is here in the C infinity category. Okay, so now, despite of the details of this theorem, which is a major theorem on linearization of non-degenerate singularities, what is important is the following. It is known that the singularities of integrable systems can be linearized, okay, if they are non-degenerate. What does this mean? This means that, roughly speaking, you have local models, okay? So this theorem is a little long and complicated to state, but if you listen to what I'm saying, I think you will find it much clearer. Singularities of integrable systems can be linearized. In which sense? You have local models near each singularity, and these local models are these. They have the following components. This is called elliptic component, hyperbolic, real component, and focus-focus component. So, for instance, suppose that you are in dimension 4, okay? If you're in dimension 4, you can put this component and another one, and this is a local model for your manifold in dimension 4. Or this component and this one. You can mix them in any way you want. The only thing is that this one, the focus-focus one, comes in pairs. Okay? So, when I say every singularity which is non-degenerate is obtained by putting together these models in an equation, this is what this formula says. Okay? But if you don't want to read the formulas now, simply keep in mind the following, what I said. Singularities which are non-degenerate can be described in terms of local models, like these ones. Okay? This is a major contribution, because it means that now, when we try to understand integrable systems, what we try to do is to see how these models interact, how they glue together. Okay? So this is crucial. Okay? Because smooth functions which define integrable systems, this is very, very general. Okay? Now, this theorem tells us that locally, integrable systems near singularities can be understood completely. And they tell us exactly which models, elliptic, hyperbolic, real, or focus-focus. Okay? So, now, I want to say, what is the notion of equality for integrable systems? So here is a proposal. Two integrable systems are, in quotation marks, equal, in mathematical terms isomorphic, if there is a symplectomorphism between them, that is a map which preserves the symplectic structure and also the structure of the fibration. Okay? So this is going to be my notion of equality for integrable systems, so to speak. Isomorphism, same form. Right? And a main classification problem in symplectic geometry is to determine which integrable systems are isomorphic in terms of invariance. Now, in view of the introductory talk I gave you at the beginning, you may have an opinion as to why this is I'm calling this, in fact, a main problem. So the reason is that, you see, integrable systems, in principle, they are very complicated objects. I'm trying to reduce them to a few invariants. So I'm trying to say this system given by these 10 functions has these 3 invariants, a polygon, a matrix, and a number. So I'm trying to reduce a system which is very complicated information to some invariance, which is simple information, in principle, simpler. Okay? This is what I'm trying to do, to find, which is typical in mathematics. You have a complicated structure. I'm trying to reduce this. I'm trying to understand what are the essential parts of this structure, okay? The invariants. So you give me 10, 20 functions on a 40-dimensional manifold, and I want to reduce that to a couple of matrices, a polytope, and some integers, okay? then you agree with me, I would have simplified greatly my problem, because this invariance completely determine the integrable system in principle. Okay? So what do I want to do next? Now I have the spectrum of an integrable system, a quantum integrable system, and I want to recover the system. What am I going to try to do? I'm going to try to compute these matrices, these polytopes, these numbers in the spectrum. Okay? You understand the strategy? So this is the strategy. You have a quantum system that has a spectrum. Okay? And now from that spectrum, I want to recover the classical system. For this, I better understand the classical system. And understanding the classical system is understanding the essential properties of the classical system, the invariance. Okay? And that's what I'm going to try to compute in the spectrum. That's why the inverse spectral problem in symplectic geometry has to combine necessarily symplectic techniques with the spectral techniques. Okay? You have half and half. You cannot, you need both. Okay? Okay, so I'm going to explain very briefly a famous type of integrable system, which is the toric integrable systems. An integrable system is toric if all the vector fields generate periodic flows. Okay? And there is a famous theorem by Atiyah and Guillemin-Sternberg that tells you that if the manifold is compact, if your manifold is compact, then the image of the system, which in principle is a subset of Rn, okay, is in fact very regular. It is a convex polytope. Okay? So you take an integrable system of this type, you do the image under the momentum map, and you don't get some arbitrary subset of Rn, you get a convex polytope. And Atiyah and Guillemin-Sternberg also gave a recipe to finding this polytope. It's the convex hull of the images of the fixed points induced by the action generated by concatenating these flows. Okay? Here you have an example. So the polygon on the left, this is the symplectic geometers will recognize this immediately as the momentum polytope of the complex projective space CP2, right? Which has dimension 4, but the polytope has dimension 3. And on the right, this polytope would be the momentum polytope of CP3. And the length of the edges correspond to multiples of the Fubini's 2D form. So, formally, if the manifold is compact, the image is a convex polytope, and this is the only invariant in this case. So two toric integrable systems are isomorphic if and only if they have the same convex polytope, up to translations and SL2C transformations. So this is very strong. Examples were known prior to this result by Costan and other authors, as Pedro Luis I'm sure knows. But this theorem tells you that a toric integrable system can be reduced to the information of a convex polytope. It's very strong. The situation is very strong. So if you see this theorem, you can ask yourself, can we go beyond this? And of course, many people wonder about this, so there are an enormous amount of papers about this. Okay, so I'm going to mention that this paper was followed by work by Thomas Delsan, who proved that not only this polytope is the only invariant of the system, but also if I give you any convex polytope, okay, if I give you any convex polytope, you can actually construct from that combinatorial information a symplectic manifold, an integrable system whose polytope associated is precisely the one you started with. Okay, so you agree with me, this is very interesting, right? So the question is, what is next? So I want to mention one point about this type of systems, which is crucial, which is that toric systems, the one I just described, cannot have components of focus-focus type or hyperbolic type. What does this mean? This means that the local models are always like this. Okay? Elliptic, regular. These are the local models of integrable systems of toric type. So you see we are missing the hyperbolic type. We're missing the focus-focus type, right? So we're missing a lot. But we can do a lot, on the other hand. We can classify them in terms of polytopes. But the types of singularities that they can have is only this type. So it reduces your local models greatly, right? Moreover, the fibers are always diffeomorphic to tori of varying dimension. So points, circles, two tori, etc. So they are always in particular submanifolds. So here is an example. These are the fibers of the integrable system corresponding to CP2. Okay? This is the polytope. This is the polytope which appears in the Atiyah-Gilleman-Sternberg theorem. Okay? Upstairs, you have three fibers, a point, a circle, and a torus. And those fibers live in a four-dimensional space, right? But they are two-dimensional, one-dimensional, and zero-dimensional. Okay, there are many works on this, on classifications of toric structures, in particular by Carson and Lerman, by Lerman-Tolman. And then there is an extension of this theory to the case of log symplectic manifolds by Gilman, Miranda Pires, and Lee Gualtieri, myself, and Tudor Ratu, which I remember working on this paper, right, Tudor? It was a very interesting and rewarding process. So this extends the toric theory to the log symplectic case. Log symplectic manifolds are, quotation marks, generalize the symplectic context. Okay, so I'm going to tell you now a very particular type of integrable system in dimension 4, which is very natural. An integrable system is semi-toric. Now I focus on dimension 4. And you may say, well, why did you go from dimension to n in the case of the Atiyah theorem, Gilleman-Sternberg theorem, and now you are in dimension 4? Well, because that's what we can do. This is what we can do. Of course, we want to go to any dimension, but this is difficult. Okay, this is difficult. So I'm going to explain now what we know about these systems. Okay, semi-toric systems in dimension 4. What does the word semi-toric suggest? Toric was that you had all functions where the two functions would generate periodic flows. So semi-toric, if you had to guess, would be that one function generates a periodic flow, right? So we have two, so one generates a periodic flow. Some technical assumptions. F1 has to be proper. The vector field generated by F1 periodic, and F does not have singularities with hyperbolic components. We are trying to remove this assumption, and I know that some of you have heard me that I'm trying to remove this assumption already for some years, right? So it is still the case, but we have made a lot of progress on this problem, okay? So there will be theorems eventually about the case of singularities with hyperbolic components. Already we have some results. Now for a discussion about the roots and breadth of the term semi-toric, you can see my paper in topology and its applications, which has just been published, dedicated to Professor Sanjurjo on his 70th birthday, who is also here, and in an hour or two is going to tell us more about the differential geometers of the Spanish Academy of Sciences. Okay, I'm going to make one more assumption, which is that simplicity. A semi-toric system is simple if each fiber of the first integral contains at most one focus point. So now I'm not going to allow a fiber pinch many times, just once. Okay? And here is an example which satisfies this condition. It's the James-Cummins model, which we saw a few minutes ago. And this has precisely one singularity of focus type, and it looks like this. Okay? And precisely one point of focus type. Now, the couple angular momenta introduced by Sadowski and Zielinski. You also, this is also semi-toric in many cases for the parameters. And if you want, you can see this in some of my papers. If you look for coupled angular momenta, you can find the details, but it's also semi-toric in many cases. And now, what is one of the main theorems I wanted to tell you is that with Sam Van Gogh, in 2009, we obtained a classification of simple semi-toric systems in dimension 4. And they are determined by a convex polygon with endpoints inside, and each with a label which consists of an integer and a Taylor series. Now, can you find here presumably this theorem contains the Atiyah theorem for this particular case of dimension 4, right? So the invariant in the Atiyah-Gilleman-Sternberg theorem was this convex polygon, right? And now we have extra information, which is we have a few points inside, and each point comes with a label, an integer label, and a Taylor series. These are the invariants, okay? The Atiyah-Gilleman-Sternberg theorem tells you your system is precisely this poly. Your system is completely determined by this polygon, okay? And now I'm saying, well, in the semi-toric case, because it's more general, there must be more, right? So the answer is there is more. And what else is there? Well, there are some points inside of the polygon, and each point comes with a label, which is an integer and a Taylor series. Now, if you had to guess, which points would you say these points are? The focus points, right? So these points which cannot appear in the toric case, right? So, just very briefly, K is an invariant which encodes the topology of the vibration. The Taylor series encodes the dynamics of the vector fields near the singularities and was constructed by Van Gogh in 2003. And the position of the points inside of the polygon is crucial, okay? So it's not that I have 3 points inside of the polygon, it's exactly where they are. That's crucial, okay? These positions determine an invariant called the height. And the proof builds on is inspired by works of many authors on singularities and affine structures, notably Arnold, Atiyah, Delsan, Dufour, Doisman, Eliasson, Gilman, Miranda, Molino, Sternberg, Van Gogh. The influences are many because the subject of integrable systems has been developing since the 18th century. So there are a great number of authors, and here I'm just mentioning some which are closer to me. Okay, so summary. You give me a semi-toric system. This is exactly all the information of your system. A polygon, in this case 3 points, and each point has an integer associated to it and a Taylor series. Okay? So we have reduced semi-toric systems in dimension 4 to a polygon with some points inside and each point with some labels. These are the invariants that I've been talking about throughout the talk. Right. So when I go to quantum semi-toric systems, I'm not going to try to compute F1 and F2, right? I'm going to try to compute this polygon, these points, and these integers, okay? So this is inspired by the theory of toric systems by Atiyah, Gilman, Delsan, Constant, and Sternberg, and the classifications of the Fomenko school, Bolsinov, Fomenko, Matveev, Oshenkov, Tabachnikov, Zung, and I'm very happy that Bolsinov is here and is going to tell us about integrable systems in his talk. And this is related also to the classification of work on almost toric systems by Simonton, Lund, Samington, Hollock, Sabatini, Sepe, and Simonton. Okay, then, if you remember, after the theorem by Atiyah, I told you a theorem by Delsan, which told you that not only the polygon is the only invariant, the polytope, but also there is a one-to-one correspondence. From each polytope, you can construct a system. So, this theorem that Sam Van Gogh and I proved tell us that this is the case for semi-toric system. system. So we start with a smooth rational polygon with interior points P1, Pn, each with a label. And one can prove that there exists a semi-toric system on a 4 manifold, which has delta and the points P1 through Pn with this label as invariance. So let me emphasize this. I give you a polygon with some points inside, and each point is labeled by an integer and a Taylor series. This is purely combinatorial information, right? And from that, from scratch, we construct an integrable system which is semi-toric, okay, that has precisely that polygon and those invariants as that polygon and those invariants as its invariants. Okay? So, summary. Semi-toric systems can be encoded exactly in this form. A polygon and some points inside with labels. Okay, so the proof, I'm not going to go to the proof, but I just want to say that this proof has some analytic components which made it challenging, which in particular, and this is an idea which happens throughout the theory of integrable systems, is that when you try to glue local models and you try to glue symplectically and smoothly, for manifolds this usually works. But when you try to glue expressions for functions, the overlaps are often extremely singular. Okay? So there is the hardest part, which I mentioned here, is after you do all this gluing of the models, you have to smoothen the overlaps where those models overlap. And this is represented here in this region, okay? So outside of, we have a few regions like this, and we have to do analysis to smoothen the system along these regions, okay? Okay. So, since I only have a few minutes, I just want to mention that there are 3 important avenues which complement each other, which are very active, which is computations of invariance, extensions of the theory in dimension 4, and moduli problems. Examples of computations. I refer you to my paper with Johan Le Floch for an example of computation for the couple angular momenta, okay? In which we compute the polygon, we compute the Taylor series. So this is not abstract information. We actually can compute it in examples, okay? And this is spread over many papers, other examples by a number of authors. Then, examples of extensions. This is a theorem that which I did with my 2 former students, Joseph Palmer and Shudi Tang, in which we extend the theorem I just told you that restricted the fibers to only have 1 pinch point to include fibers with as many pinch points as we want. Okay? So this is an extension of the theory. And it builds on work on the classification of symplectic fibers, which I did with my student Shudi Tang. And also the C-infinity classification is due to Bolsinov and Ithosimov. Then there are many other works on extensions, okay? Complexity 1 spaces, the case of hyperbolic singularities, dimensions greater than 4. There is also weaker assumptions. Most of these works are mentioned in my paper in Topology and its Applications of 2023. If you want current information, you can find it in that paper, which just got published. And many of them are also in previous papers of mine, in particular in the Bulletin of the AMS. There is a paper in 2017 which contains many of these. Okay, and I want to very briefly mention that there is also the third avenue, which is moduli problems concerning integrable systems. And I just want to mention here some works. In particular, there is a paper by myself in which I studied the modular space of toric symplectic ball embeddings. Then there is a paper that Alessio Figali and I wrote in 2016. Then there is another paper which studies this further, also with Alessio Figali and my student Joseph Palmer. And there is a paper with Tudor, Pires, and Sabatini in which we prove that the modular space of compact toric integrable systems in dimension 4 is path connected. Tudor, you remember Princeton, right? This was, in part, this was greatly advanced during visits to Princeton of Tudor. And then I'm happy to say that Paco Santos and I were able to generalize to any dimension, any finite dimension, the results in this paper. So now we have proven the connectivity of the modular space of toric integrable systems in any dimension. Did you know, Tudor, about this? Or? Yeah, okay. So I refer you to my paper in topology and its applications for some open problems. In particular, there is a problem that says study and classify contact integrable systems in the semi-toric case. There are, I think, around 30 problems, I forgot. But one of them is this, which I think is very interesting. The contact toric case was studied by Banjaga, Molino, Boyer, Galecki, Lerman, and recently Manuel de Leon and Lainz studied contact Hamiltonian systems. In my opinion, it would be very interesting to study contact integrable systems in the semi-toric case and beyond. So hopefully this is something we can do at some point. Okay. Because I gave many references, and of course it's not possible to remember all of them, I refer you to my papers in the bulletin of the AMS and my recent paper in topology and its applications. And now, if you allow me 5 more minutes, I'm going to tell you, I'm going to connect this with quantum systems, okay? So, let HK in N star be Hilbert spaces quantizing a 2n-dimensional manifold. For example, this is, as Pedro Luis knows, the Constance Oriol quantization. And in Spain, Garcia Perez was a leading expert and the central figure to the expansion of these ideas, which I believe you spoke about these ideas in the academy in particular, right? In the Spanish Academy of Sciences. So, what is a quantum integrable system? A quantum integrable system consists of n self-adjoint operators acting on Hilbert spaces, okay? Each operator is indexed by an infinite sequence k, which is the 1/h, if you like. And exactly as in the classical case, they commute and their principal symbols form an integrable system. So the very simple definition again, of course, if you know what Hilbert spaces are, semi-classical operators are, etc. And the spectrum is the support of the joint spectral measure, which if these spaces are finite dimensional, is for every k, has this form, this set of points, okay? The set, if you like, of joint eigenvalues. And then I'm going to, well, maybe I can mention this very briefly. A prequantum bundle on a symplectic manifold is a Hermitian bundle with a connection of curvature R equal omega over E, and we write h of h for the space of holomorphic sections of M into the k tensor power of this line bundle. And this is the Planck constant 1/k, okay? And these are the spaces that appear here, okay? There is a method, and people write books about this, and it's very substantial, which is geometric quantization, and explains how to construct these spaces, and Pedro Luis is an expert on this topic, so you can ask him or you can ask me. Okay, so on these spaces you can define operators, semi-classic and very syntoplis operators, and these are sequences t equal th, where h is again 1/k. So for each value, so the operator is given by a sequence of operators th, where the multiplication operator is a sequence in C infinity with an asymptotic expansion of this form for the C infinity topology, okay? And don't worry, I'm going to get to the interesting part. I just wanted to give you this setting so you know this can be made very precise, but it's very long to make this precise because there is a lot of technical aspects and a lot of content. So you can write a book surely about geometric quantization, how to construct these spaces, okay? So what is the principal symbol? The principal symbol of this operator, the principal symbol F0, which appears here, is the principal symbol of T. And of course, if you're an expert, you can ask, well, this does not define sometimes. There are many things, many details, okay? But let's assume that everything works, okay? Then F0 exists, this principal symbol, and here is the problem that has motivated much of my research, is the inverse spectral problem for quantum integrable systems, which I mentioned at the beginning. Given the semi-classical joint spectrum, XH, okay, you have one spectrum for each value of H. Okay, so for you give me 0.1, I give you a spectrum in the plane. If you give me 0.0001, I give you another spectrum on the plane, and so on. Okay, you have an infinite sequence. Given the semi-classical joint spectrum of a quantum system of integrable operators, what information can one recover about the classical system given by the principal symbols of these operators? Okay? So there has been work by many authors on this, which again you can see in my papers. And what is the strategy? The strategy is to compute the invariance of the system using spectral geometry techniques in the spectrum. Here you have the spectrum, and this is in fact the spectrum of one of the systems I mentioned earlier, the James-Cummins system, right? This is the spectrum of the quantum James-Cummins system. And you can see, if you look there, can you see this point here? There is something strange happening there, right? With the eigenvalues. So this is precisely the position of the image of the focus-focus singularity of the system. Okay, so you see, it can be seen in the spectrum. So one has to know what invariance to compute, and this we know thanks to symplectic geometry. And we use again symplectic geometry to construct the invariance of the classical system. So, for quantum toric systems, this problem can be solved, okay? And this is this theorem. Then, for quantum semi-toric systems, the problem can also be solved. And with Sam Van Gogh, and then with Johann Le Floch and Sam Van Gogh, we proved that the first four invariants of semi-toric systems, the number of interior points of the polygon, the number of interior points, the polygon, the interior points themselves, and the labels can be recovered. And recently, Le Floch and Van Gogh showed how to recover the last invariant, which was the integer k, which I mentioned. And this last result I wanted to mention because I know Pedro Luis will appreciate it, which is that in that paper we proved that toric integrable systems can be quantized. So given a classical system, you can find a quantum toric system with those symbols. And I just would like to conclude this talk by saying thank you, Pedro Luis, for all the interest in mathematical research you have produced and for having been one of the pioneers in the Spanish School of Differential Geometry and its connections to physics. This talk is dedicated to you with admiration.
There are 5 of them according to
Yes.
the classical theory, and they are not entirely equivalent. Which one is referring to? I suspect 3 and 5. I'm not sure.
So it is quite possible. I admit I don't know exactly which one, but but I'm sure you can find out.
And second question, I assume that we are always speaking of integrability in the sense of utility.
We are always speaking of
Because the
integrability.
most interesting, and there are many people working on the extension, the separative systems,
Of course.
etc., with non-commutative space, phase space.
Yes.
And then Rutwig, Domenico, Czerny-Wdzięcianski, and many others have made very interesting things with actions of the groups with many things.
Yes. Yes, thank you. Yes.
For the quantization, quantum groups play, in the sense of Trimble and Jimbo, play the key role.
Very, absolutely. Yeah. Thank you for the remarks. Yes. Thousands and thousands of papers.
he really means the Lagrange.
Uh-huh.
For sure. Yeah.
Thank you for clarification. Any other? Oh, thank you, the speaker.